Okay, so the topic is about the mean field approach for large population of stochastic control. So this means that we consider a large number of agents, so agents in a broad sense. So this could be entities, humans, or robots. So they are interacting, but they are cooperative. Okay, so in the sense that they differ from the talk by Nizar, where the agents were in strategic interaction and compete between themselves. So here, they rather act for, say, some collective welfare, okay, according to some social planner. So this is one possible interpretation. So the other possible interpretation, which we have in fact in mind for this talk, is the situation where you have an influencer who can control the state of many individuals, okay, typically in a social network. So when the number of agents goes to infinity, so this leads to the optimal control of mean field stochastic differential equation or McKean-Vlasov equation, okay, which has been extensively studied over the last year. So mostly on continuous time and finite horizon. And in this talk, I would like to focus, okay, first on a discrete time, possibly a discrete space, so you can think about graph, or infinite horizon. We also would like to consider the case where there are common noise, so this means a noise which affects all the agents, and look at the asymptotic problem when the number of agents goes to infinity, which lead to the what we call the conditional Markov Decision process. So Markov Decision process, okay, is of course the situation of stochastic control in discrete time, and conditional here refers to the fact that we have a common noise. So the motivation for considering such framework is so on one hand because it will occur naturally in application, okay, so that we'll describe in a moment. And also because it provides actually the right mathematical framework when you want to consider reinforcement learning, okay, where you have many cooperative agents, which is a topic which has been which has a growing interest and studied, for example, in these cited papers. So the application that we have in mind, in fact, come from targeted advertising problem. So you have a company, okay, so which can be viewed as an internet retailer or a candidate to election, and you have a lot of connected users, okay, browsing through a social network, where the state of each user is okay, typically either he's a customer or a voter of the C, so C could be a candidate to election or a company. And so the user's data will typically represent the cookies. So in other words, the track record of visit web page. Okay, and so in this framework, so you have the social planner here is represented by some influencer, okay, which work for the company. And so this influencer can display a personalized online banner to the users according to their cookies. Okay, so typically this influencer doesn't have access to the individual state of the user, so they don't know if the user has already bought the product or he's ready to vote for some candidate. But okay, they have a record track of his visit web page, and also there's also some public data. Okay, so this leads us to naturally consider open loop control, open loop policy, and common noise. And so the objective for the company and the influencer is to optimize the target ad strategy in order to attract the largest possible clients given some ad cost. Okay, so let me now present mathematically the problem. So some general notation. So we start from some probability space. In the following, I will denote by the state space is denoted by characteristic X, the action space by characteristic A, and on this space, though with a set of probability measure on action space, on state space, okay, and on the joint state action space that we equip with the Wasserstein distance. Next, okay, we have to describe the discrete time transition dynamics. In other words, how each agent switch from one state at time t from one state to another state. Okay, so this is modeled through some idiosyncratic noise, okay, which is personalized for each agent I. Some common noise, okay, so which are a noise faced by all the agents, and some measurable function, okay, which describe how you switch from one state to another state at from time t to time t plus 1. Okay, and so this measurable function, okay, will depend on the state, on the action, on the joint distribution of the state action and of the noise, both idiosyncratic and common noise. Okay, so we are on infinite horizon, so we have some discount factor and some reward function, okay, which is a function depending on the state, on the action, and on both distribution of state action. Some assumptions, so we made some assumption about this transition dynamics and reward. So typically a Lipschitz assumption on the transition dynamics and on the reward function. What is important to notice here is that the Lipschitz assumption on F, okay, is made on expectation. So here the expectation, okay, is with respect to the idiosyncratic noise. Okay, so it's important to make the assumption only in expectation, not pass wisely, because typically in discrete space, okay, it will be too strong and not satisfied. But when you take expectation, it's much weaker. Okay, so now the open loop control in this finite population model. So each agent starts from some initial state, and in this framework, so what is a control? So it is a sequence alpha 1 alpha n, where each alpha I represent, okay, the control followed by agent I. So it is of open loop form, so which means that it is adapted with respect to all, okay, the noise, possible noise, okay, appearing in the models, all the idiosyncratic initial state and common noise. Okay, so notice that we do not make any symmetry assumption on the control. Okay, so we do not assume that each player, each agent follows the same policy a priori. Okay, so each one can follow its own strategy. So it's why we talk about decentralized open loop control. And then, okay, we can formulate as a mean field control problem in the N population model. So it evolves according to this dynamic. So it starts from some initial state Ti, and then, okay, so here is the evolution. Okay, so from time t to time t plus 1. So the evolution depends on the current state, on the action followed by agent I. So here is the mean field aspect. So it depends on the empirical joint distribution of the state and action of all the other agents, okay, of its idiosyncratic noise and the common noise. Okay, and so this is a state for agent I. The gain functional for agent I, okay, is over infinite horizons expected cumulative reward, okay, with some discount factor beta, and the running reward, okay, depend on its state, its action, and again on the joint distribution state of all the other agents. Okay, and so the optimal gain for the social planner or also influencer, okay, will consider minimizing over all strategy alpha 1, alpha n, okay, the average, okay, of all these gain functional. Okay, so notice that if you look at such problem 1 and 2, okay, it is in fact a standard Markov decision process, okay, where whenever, okay, you consider each component x1, x2, xn, okay, so whereas now the state space will be x power n, the action space is capital A power n, for which, okay, we can in principle apply the standard methodology for solving MDP, and also for which it is known that when you maximize over open loop control or feedback control, or even if you add some randomization or relaxed control, okay, at the end you will obtain the same value. But okay, especially when n is large, okay, typically this is a difficult problem to solve, and so this is one reason why okay we are interested. Okay, people are interested by looking at the infinite population model. So when n goes to infinity, and so formally, what we expect to have as a problem is now a control McKean-Vlasov equation. So where we look at the state dynamics of some representative agent, okay, which evolve according to this equation. So now where we replace, okay, the empirical joint distribution by the theoretical conditional law of the state and of the control. So here it's conditional with respect to the common noise, okay, because everyone faces the common noise. Okay, and the gain functional for the representative agent will take this form, where again, okay, you formally replace the empirical distribution by the conditional law of the state and control with respect to the common noise epsilon 0. Okay, and so and then okay, you are interested by maximizing over all the process alpha, okay, adapted to respect to the idiosyncratic and common noise. Okay, so such problem a priori, okay, is a non-standard Markov decision process due to this dependence on the joint law of the state and the control, and this is what we call a conditional Markov mean field Markov decision process. Okay, and so the question that we would like to address, okay, in this talk, okay, is there are two main questions. So the first one is, okay, so now that we formulate, okay, the asymptotic problem, so the conditional McKean-Vlasov Markov decision process, so it is possible, okay, to obtain a tractable resolution of this problem. So for example, can we get a dynamic programming equation, a Bellman equation, which would be in fact useful for the purpose of reinforcement learning. So in other words, when you are in a model-free setting. The second question, okay, it's related to the convergence of the finite population model, okay, to the asymptotic problem. So in other words, do we have Vn converge to V, okay, first, and at which rate, okay, and on the other hand, okay, so if we are able to solve the asymptotic problem, how to get an approximate optimal control for the N-agent problem, okay, and at which accuracy. And as we shall see, the randomization of control plays a crucial role, okay, in the study of these two questions. And this is, in fact, a noticeable difference with respect to the continuous time framework. Okay, so some related literature. So as I said in the beginning, the continuous time framework has been extensively studied. But in discrete time, there are a few papers, okay, who are okay concerned with mean field Markov decision process. So there is one recent paper by Nicole Bauer, who focused on closed loop policy. So in other words, deterministic feedback control. And we shall see the difference here. I have seen also, when looking at the program, okay, I mean, the title of the talk by Amada. Okay, I haven't seen the paper, so I see that it will be tomorrow. So it's kind of advertising for the talk tomorrow. Okay, so I think that she's doing by maximum principle. Regarding the second question, so the convergence, so it has been done mostly for continuous time Markov mean field Markov decision process. Okay, so addressed by so I see the first paper who addressed this question is Daniel Lacker, okay, who prove okay by tightness arguments the convergence. of Vn towards V, but without rate of convergence. Fabrice-Jeté also extends this case to the case of common noise. With McKean-Vlasov and Varin, so we use a BSD method, in fact, to prove, in fact, the convergence of Vn towards V, but okay, under a very strong assumption that there is a smooth solution, okay, to the master Bellman equation that you get when you derive the Bellman equation in continuous time. And in this case, the rate of convergence is 1/n. And I think the most recent result about convergence result is a paper by these authors of Pierre Cardadlier, Dodin, Jackson, Sugadis. Okay, so just appeared 1 month ago, where they were able to prove, so without assuming the existence of smooth solution, okay, that the rate of convergence, okay, is of order n minus gamma for some gamma between 0 and 1. Okay, but gamma, in fact, in the paper, okay, they do not have an explicit form for gamma. They just claim that there exists some gamma, okay, between 0 and n. So the conjecture is that gamma is equal to 1, but it's still to be proved. Okay, and so we shall see, okay, what will be the case in the discrete time in this talk. Okay, so now let me address the first question, okay, about the resolution of the MDP for the mean field problem, so the conditional McKean-Vlasov problem. And so the idea, okay, is to reformulate, okay, so to lift, in fact, the problem on the set of probability measure. And so how do we proceed? Okay, so recall the dynamic of X, okay, it is in this form. Okay, and so now, okay, so I denote by mu, okay, the conditional law of X given the common noise. Okay, and so you take now the law of this equation here. Okay, so here it's mu t plus 1. And then, okay, you take the law of the pair X alpha and of the idiosyncratic noise. Okay, and so you push, okay, with the function f. Okay, so here's the star here represents the push forward of the measure notation. Okay, so this is simply by taking the law of this equation. But this is not yet a dynamics because mu appear only here, but not on the right hand side. And so the idea is, okay, to simply to use a base formula. So you rewrite the joint distribution of X alpha as the law of X multiplied by the conditional law of alpha given X. Okay, just base formula. Okay, and in this case, okay, and when you substitute this into this equation, okay, you obtain, okay, the analog of a Fokker-Planck equation, okay, but which is now control because you have the presence of the control alpha here. And notice that now this control alpha, okay, is of relaxed form in the sense that, okay, it is a value in the set of function mapping the state action space into the set of probability measure because this, okay, is a conditional probability measure. Okay, so it is value in a set of probability measure. So we see that naturally, okay, relaxed controls appear. Okay, and similarly, if you do the same kind of trick with the gain functional, okay, you can rewrite the gain functional, okay, in terms of the conditional law of X and in terms of the relaxed feedback control. Okay, so now, okay, using this transformation, okay, we have reformulated our original problem in terms of mu. Okay, so it's a Fokker-Planck equation, so evolving on the space of probability measure, and in terms of relaxed feedback control. Okay, and so the question is, in view of this reformulation, okay, so we may expect that there is a correspondence between our original conditional McKean-Vlasov MDP and the standard MDP, where now the state space will be the state space of probability measure. The action space will be the set of relaxed action space, mapping the action space into the set of probability measure. Dynamics would be f hat. The noise now would be the common noise, the reward f hat, and the discount factor beta. Okay, so this is what we formally expect. But In fact, there are some technical issue if you really want to prove this rigorously. So it is not clear that such MDP, okay, with these ingredients, okay, will be well posed in the sense that we have some measurability issues for defining f hat, small f hat, and also the fact that the relaxed control is not clear if it is F0 adapted. But anyway, there is some case where we can still prove this correspondence. Interesting case. So first, when you have common noise, okay, because if you have common noise, in this case, the MDP, okay, the lifted MDP is reduced to a deterministic control problem. Okay, so indeed, if there is no common noise, okay, so it's no more stochastic Fokker-Planck equation, it's just a deterministic Fokker-Planck equation. Okay, and so you have simply, in fact, a deterministic control problem, okay, which is well posed, there is no measurability issue. Okay, where now the deterministic state variable is a law of X. The action space is a relaxed action space. The dynamics is a well posed, and we can prove that there is a correspondence between these two problems. So in other words, if you solve this deterministic control problem, okay, you can retrieve the solution of your original mean field Markov decision process. Another case where we have correspondence is when the state space is discrete. Okay, say for example, if it has small n elements. Okay, so in this case, the lifted MDP is still well posed. Okay, because the state space can be in this case identified with a simplex. The action space can be identified with a set of probability measure power n. Okay, and so in this case, the dynamics and the rewards are measurable. And again, okay, we can prove the correspondence between the conditional McKean-Vlasov MDP and the lifted MDP on this space. So now, what about the general case? So general case means when the state space, okay, is when you have both common noise and when the state space is compact, Polish, not necessarily discrete. Okay, so it turns out that in general, okay, the lifted MDP is not well posed in the sense that you cannot find some natural algebra on the action space, on the react action space, so that the dynamics and the rewards in this lifted space are measurable, and so that the control will be F0 adapted. Okay, so it's not clear that it is well posed, but still you can consider, okay, formally, okay, the Bellman operator associated to the MDP if it would be well posed. Okay, so the Bellman operator is simply, okay, the relation which relates in a one-step transition, okay, the value function. So here we define formally the Bellman equation over infinite horizon associated to formally to this MDP. Okay, so it involves one-step transition. So f hat, okay, the one-step transition of f hat. Okay, so here everything is perfectly defined. Okay, because f hat is measurable with respect to the idiosyncratic noise. So this operator, Bellman operator, is well defined. It is contractive on the set of bounded function on the space on the function defined set of probability measure. And so there is a unique fixed point that we denote V star. Okay, and so the main result is that now indeed this Bellman equation fully characterize our problem. And so this is stated in this theorem, okay, which says that our value function, so our original value function, is low invariant. So it means that it can be viewed as a function of the law of the state, and it is equal, in fact, to the fixed point, and therefore, okay, it satisfies the Bellman fixed point equation. Okay, so this is the equation which characterizes the value function of the conditional mean field Markov decision process. Moreover, okay, we can show that for any small epsilon, okay, there exists an epsilon optimized randomized feedback control for the problem, okay, defining VX. So some remarks. So this dynamic programming equation is useful, in fact, to can be used at several levels. So it can be used first, okay, to find V by value iteration. So in other words, okay, by using a fixed point algorithm to this Bellman equation, or by policy iteration, okay, which means that okay, you iterate now the Bellman operator T A hat. It is also possible to obtain a dynamic programming equation for the Q state function. Okay, so I will not enter into the detail, but okay, this is usually what we need, okay, in order to design a reinforcement learning algorithm, okay, in this framework. Maybe just sketch of proof, because in fact it's a constructive proof. And so how does it work? Okay, in a nutshell. So first, okay, you take, okay, in the Bellman operator. So of course this supremum is not always achieved, but it can be achieved up to epsilon. Okay, so for any mu, okay, you consider some A hat, okay, which achieve as the supremum of the Bellman operator up to epsilon. And then you use some kernel randomization, which means that you construct, okay, some function defined on the state space with an argument 0, 1, so u, such that when you take the distribution of this function, when you follow a uniform random variable, okay, it follows the distribution of A hat, the relaxed control. Okay, and then this is the main technical point. You show through some measurable copying result that such mapping, okay, which define this function above, okay, is measurable. And from this function, okay, you construct some randomized feedback control. Okay, so what is this randomized feedback control? So it is a function depending on the conditional law of the state, and of some uniform random variable. So it means that at each time, okay, you flip a coin, and depending on the realization of this coin, okay, you inject in this function, and this gives you the value of your control. So it's why, okay, we call this a randomized control. And this randomized feedback control, okay, will be an epsilon optimal for your value function. Okay, so now third point about the convergence. So the second question that I would like to address in this talk is about the convergence of the finite population model to the asymptotic problem. Okay, so usually how we prove is you rely on some propagation of chaos on the state process, okay, toward its asymptotic limit, either in a pathwise way or in law. And for this, you usually rely on symmetric arguments, okay, and then you deduce the convergence of the value function toward the value function in the asymptotic problem. But here, we do not have, in general, propagation of chaos on the control process, which is controlled by the alpha 1, alpha n, because typically, as I said in the beginning, okay, our control is not symmetric. Okay, we do not impose that the alpha 1, alpha n follows the same policy a priori. Okay, so it means that, okay, we cannot a priori expect to be able to prove a propagation of chaos directly on the state process. And so to overcome this point, okay, instead, what we prove is a propagation of chaos on the Bellman operator. Okay, so in other words, okay, you consider the Bellman operator associated to the N-agent problem. So the N-agent problem, as I said in the introduction, is a standard MDP. Okay, so on the state space Xn R capital N. Okay, so you can consider, okay, it's a Bellman operator, okay, which take this form. Okay, but it's a long notation, but it's the standard Bellman operator, which of course depends on capital N, whereas action is a value in Rn. And then, okay, we prove, okay, a propagation curve of this Bellman operator. And so how does it, is it stated? So recall that V is the value function of the asymptotic prime, so the conditional Markov infin process. Okay, so given V, okay, we define this function var theta n. So it is a function defined on xn. Okay, so it is simply the value function evaluated for the empirical measure of x. Okay, and so the result, okay, is the following. So if you take the sup, so this is the sup, okay, which appear in the Bellman equation for the infinite population model, and here it is a sup, the Bellman operator, okay, in the asymptotic problem. Okay, so evaluated along the empirical measure. So if you evaluate the difference between these Bellman operators, okay, so it is bounded by so capital MN&gamma. So what is MN? So MN is the rate of convergence, okay, of the empirical measure toward its theoretical measure. Okay, so this quantity is known to converge towards 0. Okay, and so now from the well-known paper by Fournier and Guillain, we even know the rate of convergence of MN. Okay, so which I recall here and which typically depend on the dimension of the state space. And moreover, okay, you have this this power exponent gamma. So what is gamma? So gamma is here. Okay, so it is a minimum between 1, absolute value of log beta. So I recall that beta is the discount factor, and kappa kf. So kf is the Lipschitz constant. Okay, that I made in the beginning. Okay, in the Lipschitz condition for the transition dynamics. Okay, and so here it means that you have okay the explicit rate of convergence for the Bellman operator, and so the consequence. So this is what we are interested. Okay, is on the problem. So first on the value function. Okay, which says that okay the value function Vn converge to V. Okay, which is the rate of conversion Mn power gamma. And moreover, okay, second point about the optimal control. So now if you take an optimal, or more precisely, an epsilon optimal randomized feedback control for the asymptotic prime, so the conditional McKean-Vlasov MDP, then okay, you can construct okay an epsilon plus big O of Mn power gamma optimal randomized feedback control for the N-agent MDP. And so how is defined this randomized feedback control for the N-agent prime? So it is you take the function A epsilon evaluated according to the empirical measure of all your agents, the state space of agent I, and for each agent I, okay, you flip a coin, okay, UI, and then okay, this gives you the realization alpha I for agent I, okay, and so this means that in fact, policy to agent in the population are applied randomly by the central planner. Okay, so for each agent, okay, you follow first this classical deterministic policy, but okay, you flip a coin UI. Okay, this means that a priori the agent will have a non-symmetric assignment. Okay, which is rather natural when you have a large population of agents. You do not want to assign the same policy to everyone. Okay, you want to add some randomization. Okay, in order to be that way. I mean, it will be more efficient, optimal. Okay, so this is for theory. So now I would like to come back, okay, for the rest of the talk to the application that I have mentioned at the beginning, and to illustrate at some points our result. Okay, so back to the targeted advertising example. Okay, so in this example, okay, the state space is simply 0, 1. So state 1, okay, means that the user, okay, is customer or not of the company. The action space, okay, is simply 0 or 1. So 1 means that the influencer display an ad, and 0 means that it does not display an ad. And so for each user I in the social network, So for example, we interpret the idiosyncratic noise epsilon IT as some uniform random variable representing, for example, the time spent at day t, okay, on a forum talking about the product sold by C. Okay, the idea is that the more time he spent on such forum, okay, the more chance he has to be influenced, okay, to buy or to vote for candidate C. Okay, and so for simplicity here, there is no common noise. And so now, if we look at, so now the target, the dynamics and the reward. So here, the dynamics, okay, F, okay, so it's a function, a value in 0, 1, because state is 0, 1, so it will be of indicator form. And so we take this form. So what does it mean? So for example, if his state is 0, okay, this indicator means that the interpretation is the following. So he has more chance, okay, to switch to state 1 if, okay, he spends a lot of time in the forum, and if the proportion of users that are not customer of C, so mu of 0, is small, okay, and if he has received an ad, and if the efficiency of the ad, okay, represented by the parameter eta is large, okay, and then, okay, he has more chance, okay, to switch to state 1. On the other hand, if he is already a customer of 1, okay, so he will have, okay, he will probably have more incentive to stay in this state 1, okay, if E is small, so it means that he has not spent a lot of time on the forum, and if there's already a lot of users around him who are customer of C, so you want to follow the trend, and also if you have received some ads. Okay, and for the reward function, we take a very simple reward function, the linear. So each time you receive, each time he has converted a user, he gains the reward X, and he has to pay a cost, okay, with some ad cost, capital C, small c. Okay, so now, okay, so a priori we can write the N-agent prime with this notation, but in fact, if we look at the asymptotic prime, it's much more simpler. So if we look at the lifted problem, so when you lift on when n goes to infinity, in this case, okay, the variable which is relevant, in fact, because state is 0, 1, is in fact the proportion of users that are customer of C, and now the relaxed control Q, okay, will be the probability of displaying an ad to the users. So, or equivalently, okay, so if you send an ad to a proportion QT of the users, okay, and then if you look at the Fokker-Planck equation, the stochastic Fokker-Planck equation, in this example, this simple model, it takes this form, okay. So here is the dynamics of the proportion of users, okay, who become customer of C, in terms of the control Q, and here is the value function. Okay, so this is a deterministic control problem, which can be in fact explicitly solved. Okay, and the solution in fact depends. So there is a disjunction depending on the ratio cost over efficiency. Okay, so what does it mean? It means that if the ad cost, the ratio of ad cost with respect to the ad efficiency is small enough, so meaning that if the ad is very cheap, okay, so actually smaller than beta, then it is optimal, okay, to always send an ad to the whole population, except at the end when you have enough, you consider that there are enough people who are already customer of C, and then, okay, it is not worth anymore to send ad. On the opposite side, if the ad is too expensive, so namely larger than beta divided by 1 minus beta, then, okay, it is too expensive, and then the optimal control, okay, would be to never send an ad. Okay, and so the interesting case, in fact, is between these two values, where the optimal control is precisely neither nor 1 or 0. So it is between 0 and 1. So in other words, it is in fact randomized. So you send an ad, but not to the whole population, but okay, only to a proportion QT of the population. And so let me now focus on this case. And so here this graph, okay, depicts the form of the optimal control. Okay, so here it is the form of the optimal control Q star in function of the proportion of users that are customer of C. Okay, so we see that if P is small enough, so in this region, then okay, you send an ad to the whole population. But there is a region where here, okay, when P is not too small, not too big, okay, when you send only you send this ad, okay, such quantity, okay, to the ad. So it is strictly smaller than 1. Okay, and then okay, at the end, okay, when P is almost close to 1, okay, then okay, it is irrelevant to send an ad to the population and just never send, okay, just send 0 to the rest of the population. Okay, so maybe it's more to visualize more precisely the form of the evolution of the proportion of users. So let us look at the optimal increment of PT. Okay, so in other words, the evolution of PT plus 1 minus PT in function of PT. Okay, and so here it's the maximum, but you see that here, okay, you do not send the maximums as we have seen in the previous slide. Okay, so which means that, okay, so for example, okay, if at the initial time you have such proportion of users that are customer of C, then okay, the next step you put this increment, okay, which means that the next value of the proportion is P1. Okay, then okay, you increment by this quantity, okay, and then the next value is P2, okay, and then you increment by such quantity, okay, and then at the end, okay, you will be able, okay, to reach the whole population. Okay, and so here you see in particular why it is crucial indeed to use randomized strategy, because in fact, if you always use deterministic policy, okay, you would never be able to reach the whole population, because for example here, if you at this point, okay, you increment using the Q equal 1, okay, you will at the end, okay, you will be stuck into this region and then never be able to reach, okay, the whole population. Why? You see that by using randomized strategy, okay, at the end you are able to, okay, to convert at some point the whole population. Of course, this is a simple toy example, but to illustrate, okay, why okay, randomized strategy, okay, is more efficient than deterministic policy in this framework. Okay, so now, okay, let me summarize the main result of this talk. So what we have shown is that, okay, we can lift the conditional Markov Decision process to an optimization problem on the space of law with relaxed control, okay, with 3 different situations. So when there is no common noise, okay, so in this case, the lifted problem is a deterministic control problem, but of course, on the space of probability measure and relaxed action space, for which, okay, the resolution can be more or less standard, and sometimes we can find explicit solutions. So this is precisely the example that I have shown you for the target advertising. When you have common noise and the discrete space is finite, okay, so the lifted problem becomes a MDP on the simplex, for which, okay, you can apply again standard methodology of MDP. And in general, okay, you always have a characterization of your lifted problem in terms of a Bellman equation or fixed point equation. And also you have an epsilon optimized randomized feedback policy, which can be computed either by policy or value iteration. So we have proved the convergence of the N-agent problem to the asymptotic problem with a rate of conversion which is explicit. And also we have shown how an optimal randomized feedback control for the asymptotic problem provide okay, an asymptotic, an optimal control for the N-agent problem. Okay, and some final remarks, okay, concerning, okay, the distinction between open loop versus feedback and randomized feedback control. Okay, so in standard MDP, okay, it is well known that when you take the supremum over open loop feedback, randomized feedback control, okay, it provides always the same value. Okay, so maybe you have existence for a problem and not for the other one, but the soup is the same. Here, okay, what we have shown is that when you add mean field dependence, so what we show is that, okay, if you take the supremum over open loop control, okay, it is equivalent to the supremum over randomized feedback control, and the supremum over randomized feedback control is strictly larger than the supremum over feedback control. Okay, and so this is really a difference with respect to the continuous time mean field control problem, where, okay, we know that randomization, okay, does not yield a greater gain. Okay, so just last slide. So for the reference, so most of this talk is based on this paper. Actually, in fact, in this paper, okay, we prove the result, but by considering a symmetric control, in the sense that all the agents follow the same policy. Okay, what I have presented in this talk is a case, more general case, where all the alpha I are decentralized, so not necessarily symmetric. So this is mainly developed in the thesis of Melik Mott, together with the applications that I've show you in the last part of this talk. Okay, and so I thank you for your attention.
So thank you for the very dense, with many things introduced talk. Now open for questions, impressions from the audience, impression from the virtual audience as well.
Well, thank you very much for the talk. Just really, it's comment, not a question. I have a couple of papers with this one over N-gamma convergence rates, so it possibly would be interesting just to compare. Yes, what is in your
continuous time also?
Huh?
In continuous time.
Continuous time, yes,
okay,
continuous time, yeah. Yeah, but there is also remarks there on discrete time, which somehow not exactly the same setting, but very similar, in fact, and rather general finite state space. Okay, thank you.
For pointing out.
More comments? So I have a question myself, starting from the end. This toy example. Now you have taken no common noise.
Yes.
But how much more complicated, and what would be the feeling with the common noise in this one? Because that would be fully random, stochastic, right?
Yes. If you have a common noise, in this case, you will have a real stochastic control problem. I think in the thesis, okay, Médéric developed the calculation, so it's not so explicit, but you can have some quantitative result about at least the structure of the solution. So basically, you still have this distinction concerning the solution, but probably it's not so more explicit. But you can say some, you can characterize through some equation or PD. So you have instead a partial differential equation to solve in this case, but in terms of difference equation, but it's it can be dealt with.
Okay. I also had another small question about this performance, or what is called the value functions that is taken on time up to infinity.
Yes.
So is there some limiting at the limit conditions and how this impact?
What do you mean?
So all these value functions have time is a series, no?
Yes,
time to infinity. Yes. So there is some kind of assumptions on the decay or limit conditions there.
Yes.
How much restrictive this become into?
Yeah. So for so here we assume that in order to ensure that the problem is well posed, that the F is bounded, the rarr is bounded. Well, so in the example, because the discrete space, the space and action pair are discrete, so it's not an issue. And also because recall that the action and the state space are compact. So I think it's not really a big issue.
Okay, other comments? The audience? No? In virtual audience? No? Then we thank Huyen for his talk.
Thank you.
And we start getting